You can answer this question with a single word: gravity. The weakest force in the universe is gravity. But that answer feels wrong, doesn't it? It feels completely backwards. Gravity is the force that holds you to your chair. It keeps your feet on the ground, it holds the moon in orbit around the Earth, it holds the Earth in orbit around the sun. And gravity pulls entire galaxies together into massive clusters. It seems powerful. It seems like the boss. And yet, it's not. It is the weakest of them all. And it's not just a little weaker. It's weaker by a margin that is almost impossible to comprehend. The gap between gravity and the next weakest force is vaster than the gap between a single grain of sand and all the stars in the known universe. To understand why, we need to talk about what we mean by force. In physics, there are four fundamental forces of nature. These are the basic interactions that govern how everything in the universe behaves, from the smallest particles to the largest galaxies. Everything that happens, every push and every pull, every chemical reaction, every star that shines, is a result of these four forces at work. They are the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Let's look at them one by one, starting with the strongest. The strong nuclear force is the true heavyweight champion of the universe. It's the force that holds the universe together at its most fundamental level. You are made of atoms. The center of every atom is a nucleus. That nucleus is packed with particles called protons and neutrons. Now, protons have a positive electrical charge, and if you remember anything from science class, you know that like charges repel. Two positive charges want to fly apart from each other. So the nucleus of an atom packed full of positively charged protons should be an impossible object. It should instantly blow itself to pieces. The reason it doesn't is the strong nuclear force. This force is incredibly powerful. It acts like a kind of cosmic superglue. It binds the protons and neutrons together, overcoming the immense electrical repulsion between the protons. It's what makes atomic nuclei stable. Without the strong force, there would be no atoms more complex than hydrogen. No chemistry, no planets, no people. The universe would just be a thin soup of individual particles. But the strong force has a major limitation. It only works over incredibly short distances. Its reach is confined to the scale of an atomic nucleus. If you pull two protons apart by just a little more than their own width, the strong force between them drops to zero. It's like the strongest Velcro in existence. When it's stuck, it's almost impossible to unstick. But move it a tiny fraction of an inch away, and its power is gone completely. This is why we don't feel the strong force in our daily lives. Its influence is trapped inside the atoms that make us up. Next in line is the electromagnetic force. This is the force you are most familiar with, even if you don't always think about it. It's the force of electricity and magnetism. They are two sides of the same coin. This force is what makes a magnet stick to your refrigerator. It's what makes static electricity crackle when you take off a sweater. It's what powers the lights in your room and the computer you're using, but its influence is much deeper than that. The electromagnetic force is responsible for basically all of chemistry. It's the force that binds electrons to atomic nuclei, allowing atoms to exist. It's the force that links atoms together to form molecules. The chair you're sitting on is solid because the electromagnetic forces between its atoms are repelling the atoms in your body. The very signals traveling through your nerves to your brain are an electromagnetic phenomenon. Light itself is a wave of electromagnetism. Compared to the strong force, electromagnetism is weaker. It's about 137 times weaker, to be specific, but it has a huge advantage. Its range is infinite. It gets weaker with distance, of course, just like the light from a candle gets dimmer the farther away you are. But it never truly drops to zero. The electromagnetic force from a single electron technically reaches across the entire universe. A key feature of this force is that it can both attract and repel. There are positive charges and negative charges. Like charges repel and opposite charges attract. This is important because in most large objects like you or the Earth or the Sun, the number of positive charges, protons, and negative charges, electrons, is almost perfectly balanced. They cancel each other out. This is why you don't feel a strong electrical pull from every object you walk past. The net charge is neutral. Then we have the weak nuclear force. This one is a bit strange. It's much weaker than both the strong force and the electromagnetic force. As its name suggests, it's weak. But its job is crucial. The weak force is responsible for certain types of radioactive decay. It has the unique ability to change one type of subatomic particle into another. For example, it can change a neutron into a proton, an electron, and another particle called an antineutrino. This process is fundamental to how the sun works. The sun generates energy by fusing hydrogen nuclei together to make helium. This process couldn't happen without the weak force stepping in to change protons into neutrons along the way. Without the weak force, stars wouldn't shine. The elements heavier than hydrogen that were forged in the cores of ancient stars would have never been created. Like the strong force, the weak force also has an extremely short range. Its influence is even shorter than the strong force, confined to distances smaller than a single proton. So, again, you never feel it directly. It does its work in the hidden, subatomic world. It's the quiet force, changing the identity of particles in the dark. And that brings us back to gravity. Gravity is the last of the four forces. It's the one we experience most directly and constantly. It is the force of attraction between any two objects that have mass. You have mass, so you pull on the Earth. The Earth has mass, so it pulls on you. The Earth's pull is a lot more noticeable, of course. Like electromagnetism, gravity has an infinite range, and like electromagnetism, it gets weaker with distance. But gravity has a critical difference. It only attracts. There is no such thing as negative mass or anti-gravity. Every bit of mass and energy in the universe pulls on every other bit of mass and energy. There's no cancellation. You can't have a gravitationally neutral object. This is why gravity dominates on the largest scales. While the electromagnetic forces in a planet are all neatly canceled out, every single atom in the planet adds its tiny gravitational pull to the total. All those tiny pulls add up. On the scale of planets, stars, and galaxies, gravity is the only force left in the game that has the range to do anything. The strong and weak forces are too short-ranged, and the electromagnetic force has canceled itself out. So gravity, despite its weakness, gets to shape the cosmos. So how weak is it really? Well, let's go back to that magnet on your refrigerator. Think about what is happening in that simple act. A small, cheap magnet, maybe an inch across, is holding itself to the door. What is it fighting against? It is fighting against the gravitational pull of the entire planet Earth. The whole planet, 6 trillion kilograms of rock and iron, is pulling that magnet downwards with the force of gravity. And yet, the tiny bit of organized electromagnetism in that little magnet is winning. The electromagnetic force in that magnet is stronger than the gravitational force of an entire world. That gives you a sense of the difference, but the true numbers are even more mind-boggling. And physicists like to compare the strength of the forces between two simple particles, like a pair of protons sitting next to each other. If we say the strong nuclear force has a strength of 1, just to set a baseline, then the electromagnetic force has a strength of about 1/137. It's weaker, but still in the same ballpark. The weak nuclear force has a strength of about 1/1,000,000. That's a big drop. It is truly weak. And then there's gravity. The gravitational force between those two protons has a strength of about 10 to the power of -38. Let's write that out. It's a 0. Followed by a decimal point, followed by 37 more zeros, and then a 1. To put in perspective, if the strong force was the size of the entire observable universe, the force of gravity would be the size of a single human hair. The weakness of gravity is not just a curiosity. It is the single biggest mystery in modern fundamental physics. It has a name, the hierarchy problem. The problem is not just that the forces have different strengths. The problem is, why is the gap so enormous? Why is gravity so ridiculously, absurdly, unnaturally weak compared to the other forces? The other three forces, while different in strength, feel like they are related. Their strengths are, in a cosmic sense, somewhat comparable, but gravity is the odd one out. It's like 3 people standing together and a 4th person on the other side of the galaxy. They are not in the same league. They are not even playing the same sport. Physicists don't like this. In our theories of the universe, a number that is so wildly different from all the others usually means one of two things. Either it's a complete coincidence, a random fluke of nature, which is a deeply unsatisfying answer, or it means we are missing something profound about how the universe works. There must be a reason for this weakness, and discovering that reason could change everything we know about physics. So, what are the possible reasons? Scientists have come up with several fascinating and very strange ideas. One of the most popular ideas comes from string theory. It's the idea of extra dimensions. We are used to living in a world with 3 dimensions of space length, width, and height, and 1 dimension of time. But what if there are more? What if there are tiny, curled-up dimensions of space that are too small for us to see or interact with? According to this idea, the other 3 forces, strong, weak, and electromagnetic, are stuck to our 3-dimensional brain, which is our slice of the universe. They operate only within our dimensions, but gravity is different. Gravity, according to this theory, is not stuck. It is free to spread out into all the dimensions, both our big ones and the tiny hidden ones. Imagine shouting in a small room. Your voice seems loud because the sound is confined. Now imagine shouting in the middle of a huge open field. Your voice seems much weaker from a distance because the sound spreads out in all directions. The extra dimensions idea says something similar is happening with gravity. The true strength of gravity might actually be similar to the other forces. It might not be weak at all. But because its force is leaking out into these other dimensions, we only get to feel a tiny diluted fraction of its real power here in our 3 dimensions. The other forces seem strong because their full strength is confined to our world. Gravity seems weak because we're only experiencing a faint echo of it. It's a wild idea. But it provides a potential mathematical solution to the hierarchy problem. It explains the apparent weakness of gravity not as a fundamental property of the force itself, but as a consequence of the shape of the universe we live in. Scientists at places like the Large Hadron Collider have looked for evidence of these extra dimensions, such as energy seeming to disappear from particle collisions, leaking into another dimension, but so far they haven't found anything conclusive. Another way to think about gravity is through its messenger particle. The current theory of particle physics, called the Standard Model, describes the forces as being carried by particles. Electromagnetism is carried by photons. The strong force is carried by gluons. The weak force is carried by W and Z bosons. These have all been discovered and studied. The theory predicts that gravity should also have a messenger particle, which has been named the graviton. But because gravity is so incredibly weak, these gravitons would interact very, very rarely. They are almost impossible to detect. We have never found one. Trying to detect a graviton would be harder than trying to find one specific grain of sand on all the beaches of the world. So, part of the mystery is tied up in the nature of the graviton itself. Why does it interact so weakly with matter compared to photons or gluons? Or is it fundamentally different? Does it have properties we haven't even imagined yet? The weakness of gravity also has profound implications for the universe we live in. In a way, we are very lucky that gravity is so weak. Think about what would happen if it were stronger. If gravity were, say, as strong as the electromagnetic force, the universe would be a completely different place. It might not even exist. The Big Bang, the event that started our universe, was a delicate balance between an outward expansion and the inward pull of gravity. If gravity had been much stronger, it might have immediately pulled everything back together into a big crunch before anything had a chance to form. The universe would have been over in an instant. Even if the universe survived that initial moment, life would be impossible. Stars are also a delicate balance. The outward pressure from the nuclear fusion in their core pushes out, while the inward pull of gravity tries to crush them. If gravity were much stronger, this balance would be thrown off. Stars would have to burn their fuel at a much faster rate to fight against the crush of gravity, or they would be far hotter and would burn out in a few million years, or even less. That's not nearly enough time for a planet to cool down and for complex life to evolve. Our own sun has been shining steadily for nearly 5 billion years, giving life on Earth the time it needed. This long, stable lifespan is a direct consequence of the weakness of gravity. On a smaller scale, if gravity were stronger, everything would be crushed. A planet the size of Earth would have such intense surface gravity that complex structures couldn't exist. Trees couldn't grow. Animals of any size would be flattened. Even atoms might have trouble holding themselves together against the gravitational shear. So the weakness of gravity is not a flaw in the design of the universe. It is a critical feature. It is the thing that allows for complexity and structure. It slows everything down. It allows for the universe to be vast and long-lived and interesting. It sets the timescale for the cosmos. The strong force sets the rules for the nucleus. The electromagnetic force sets the rules for atoms and chemistry. But gravity sets the pace for the universe itself. This connects to another deep idea in physics called the anthropic principle. It's the observation that the laws of nature seem to be finely tuned for the existence of life. If you change the strength of any of the 4 forces by just a small amount, the universe would be sterile and dead. If the strong force were a little weaker, nuclei wouldn't hold together. If it were a little stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for long-lived stars like our sun. If gravity were different, as we've seen, the consequences would be catastrophic. Some see this fine-tuning as evidence of a deeper purpose or design. Others see it as a selection effect. Maybe there are countless universes, a multiverse, each with different physical laws and force strengths. We just happen to find ourselves living in one of the few universes where the conditions are right for life to exist because, well, We couldn't exist to observe it otherwise. In all the other universes where gravity is strong, there's nobody around to wonder why. This is still a topic of debate, bordering on philosophy as much as science. But the hierarchy problem, the question of why gravity is so weak, is a concrete scientific puzzle. It points to a crack in our best theories of the universe. The standard model of particle physics, which describes the other three forces with incredible precision, has no place for gravity. Our best theory of gravity, Einstein's general theory of relativity, describes gravity not as a force in the same sense as the others, but as a curvature of space-time itself. Einstein imagined space and time as a single, four-dimensional fabric. Massive objects like planets and stars create dents, or warps, in this fabric. Other objects moving nearby follow these curves, which we perceive as the pull of gravity. A planet orbiting the sun isn't being pulled by an invisible rope. It's following a straight line through curved space. This geometric view of gravity is beautiful and has been confirmed by every experiment we've thrown at it. But it's fundamentally incompatible with the quantum particle-based view of the other three forces. We don't have a working theory of quantum gravity that can unite them. Physicists believe that solving the hierarchy problem is a key step towards finding this ultimate theory, a theory of everything that could describe all four forces under a single mathematical framework. So, the next time you drop a pen on the floor, you are watching the weakest force in the universe in action. It seems powerful because it is the collective pull of an entire planet, every single atom working together. But remember the fridge magnet? Remember that the tiny invisible dance of electrons in that magnet is enough to defy a whole world. The weakness of gravity is a profound and humbling fact. It tells us that the universe we see, the one of stars and galaxies, is governed by a force that is almost unimaginably feeble. And it presents us with a giant question mark right at the heart of our understanding of reality. It's a hint that there is more to the universe than we can see, whether it's hidden dimensions, new particles, or a new understanding of space and time itself. The weakest force is, in many ways, the biggest mystery, and solving it might be the key to understanding everything else.